Hello everyone, this is Dr. Hopkins with the next super exciting video in our series of videos for 106. Today we are going to deal with bases. So for strong bases, we wanted to determine the pH, and I think we've already done this, but let's review. So remember, strong bases are all of our soluble hydroxides. So let's take the easiest one to do, sodium hydroxide. Let's determine the pH of a 0.25 molar sodium hydroxide solution. So we know the sodium hydroxide and the hydroxide concentration are the same, so our pH is just going to be 14 minus the negative log of 0.25, because pOH is the negative log of 0.25, or OH minus concentration, and so that pH is 13.4. Pretty simple, because we know with strong bases there's a complete dissociation into OH minus. Now what about if we have a weak base? So in this case, we've got to write a base dissociation equilibrium expression, okay, as opposed to weak acids where we wrote an acid dissociation. This is a base dissociation. So we've got NH3 as our weak base. H2O is going to act as our acid, so base plus acid. Then the conjugate base of H2O acting like an acid is OH minus. And the conjugate acid of NH3 is NH4+. Remember, we need to remember our conjugate acid base pairs. So I looked up the equilibrium constant. Now in this case, they're going to be KBs. We would look up tables of KBs, and for this, it's 1.8 times 10 to the minus 5. Or if you look up various sources, it can be something like 1.76. Oftentimes, depending on where you get it from, there are small variations in the equilibrium constants that you'll see. But most of the time they're pretty small. All right, so our KB expression for this equilibrium, so it's products, OH minus and NH4 plus concentration over reactants, NH3, H2O is a pure liquid, it doesn't factor in. So let's solve this for the pH of a 0.1 molar ammonia solution. All right, so now we have our base dissociation expression set up. We've got our ICE table. This is an equilibrium. It's weak. We are going to start out with an initial concentration of 0.100. H2O, we don't care because it's not in the equilibrium. And then OH minus, we start with 0 and 0 in our initial. Okay, and then we, just like the acid dissociation, we set up our algebra, minus X plus X and plus X, and so our equilibrium concentrations of those two are X, and this is 0.1 minus X. So then our KB is equal to, like we wrote on the previous slide, NH4 plus over NH3, and that's equal to 1.8 times 10 to the minus 5. Okay, and so we plug in X, and then this is 0.1 minus X, but I'm going to do something at this point, so that because this is 1 times 10 to the minus 10, or 10 to the minus 1, and this is 10 to the minus 5, I'm going to go ahead and make an assumption. I'm going to assume that X is small compared to 0.1. Now we need to check. We need to check this at the end, but we're going to make this, it's going to make the math a little simpler. So we've got 1.8 times 10 to the minus 5 equals X squared, and now this will just be 0.1. And now we solve for X, and then X in this case is just 0.1 times 1.8 times 10 to the minus 5. Take the square root, and we get something on the order of 1.3 times 10 to the minus 3 is our X from this value. And that is the same thing as our OH minus concentration. It's also our NH4 plus, not that we care about that at this point, because we're just going to worry about this. Okay, so now we have our OH minus. Now the big trick with the base dissociation is, notice we don't have H3O plus. We can't just take the negative log of our answer and get the pH. that we can get the pOH. So our pH is equal to 14 minus the pOH. So that would be 14 minus the negative log of 1.3 times 10 to the minus 3. Okay, and if we do that, we get something on the order of 11.12 or so. So we have a pH of 11.12 in this case. And so that's how you do base dissociation in water problems. It's just an additional step beyond what you would have done for Ka. All right, now that we've solved a base dissociation and we know how to do a Kb calculation, we've been using this principle that 14 is equal to the sum of the pH and the pOH. And at one point, I think I promised that we would derive this. Well, the time has come to actually derive this. So our conversion from pOH to pH goes through water. So let's start with the autodissociation of water. So if we have H2O as an acid, H2O plus as a base, we're going to generate H3O plus, the conjugate acid of the base, and OH minus, the conjugate base of the acid. Okay, so that's our reaction. We've seen this before. Now, what we hadn't seen is that there's an actual equilibrium constant for this at room temperature and so forth, Kw, and that's 1 times 10 to the minus 14. And so I've also written the Kw expression from our concentrations. And notice it's just the product of the products. The reactants are all pure liquids and don't factor into the equilibrium. So let's take the negative log of this whole equation. And if we do that, we get the negative log of Kw, the negative log of H3O plus. Now remember, if you take the log of a product of values, so if you take the log of xy, it's the same thing as log x plus log y, so we've done the same thing here. So we have the negative log of H3O plus, the negative log of OH minus, which are both the pH and the pOH. And now I put a P in front of the Kw just to be consistent. So pKw is equal to pH plus pOH. If we plug in the 10 to the minus 14 into the negative log, 14 is the sum of the pH plus the pOH. So why don't we solve this? What's the pH of pure water? So now we have the autodissociation problem set up. We have our two H2Os on the reactant side. Our products are H3O plus and OH minus. This is actually quite a simple. We really don't even need to set up an ice table, but I will, just because that's our process. So we have initial concentration. It doesn't matter. It doesn't matter because those aren't factor into the equilibrium. So we consider our initial concentrations of our products to be 0, and then we're going to add in X because they're 1 to 1, and so each one of them are X. We plug those in to our Kw, which is 1 times 10 to the minus 14. So that means 1.0 times 10 to the minus 14 equals X squared. We don't need a calculator to do that math. The square root of that is equal to 1.0 times 10 to the minus 7. So that is my H3O plus concentration. It's actually also my OH minus concentration. Now this is a pretty small number, 10 to the minus 7. But if we were to figure out the pH, we just take the negative log, and it's 7. So remember when we talked about neutral, the acid and base are balanced. Pure water will give you a pH of 7. And lastly, we have our key takeaways from this video. Basically, we've set up base dissociation equilibrium. Still the same thing, acid plus base equals conjugate acid plus conjugate base. But in this case, we're focused on the base itself. It's Kb. We once again use ice tables. We get a pOH. We convert to pH through the Kw, which we now know the Kw for water is 1 times 10 to the minus 14. And that's going to come into play in the next few lessons or videos. So until next time.